All right, so welcome to Deep Learning with TensorFlow and Earth Engine. This is kind of a follow-on from the previous talk that was downstairs in Endeavor with Noel and Emily. I'm Nick Clinton, and we also have...
Hi, I'm AGV. We're both developer relations engineers for Earth Engine. Just a quick shout out, David Cavazos is another amazing peer of ours who wrote an end-to-end sample that you will be able to visit today, but he's not on stage, so just a quick shout out to him as well.
All right, thanks. One thing I forgot, get this link, TF2_G4G_22. That is the link to these slides. There are tons of other links to Colab notebooks and docs and code editor links and so forth from the slide deck. So you're probably going to want that link. TF2_G4G_22. Somebody remember that.
Or take a picture. I'll also show it at the end.
All right. Let's just dive right in because we've got a lot of content here, and we're going to try to get through it all without going over. So we're going to talk about a bunch of things here. The first is just options for getting training data out of Earth Engine and training a model with it. We'll talk a little bit about what deep learning is and the architecture of models that you would use to implement deep learning in TensorFlow. And then we'll have a short demo of some working land cover classification examples, and then we'll just wrap up from there. Okay, so as I mentioned, this is a follow-on from the previous one. If you weren't in Endeavor this morning, those slides will be online, but that's sort of a gentle introduction to machine learning with Earth Engine. There are lots of options for training a model. Oops, okay, there we go. Options for training. Lots of options for training a machine learning model in Earth Engine. And we like to use a lot of food analogies. So, the built-in Earth Engine classifiers, like the random forest models that they were talking about earlier, are not very spicy. Noel showed you 8 lines of code. You can implement a random forest in 8 lines of code. But if you've got an appetite for spicy food, you might love TensorFlow. And that's primarily what we're going to be talking about here. You can build much spicier models with TensorFlow. So, again, basic stuff built into Earth Engine with any machine learning or data mining problem. Often you start with a simple model that lets you understand the data. That's a great use for these Earth Engine classifiers. These include random forest cart, naive Bayes, support vector machines, and unsupervised classifiers or clusterers. These are definitely very easy to use and get running quickly. But there are options for training and predicting in the cloud if your model gets too large or your training data set gets, whoops, sorry. Here, I got it. Okay, so another food analogy. Let's say you want to have a cake. You can just go to the market and buy a cake, like off the shelf. That cake might be fine for you. But if you're good at cooking and you want to make like a really fancy cake or maybe a gingerbread house or something like that, you've really got to build it yourself. And so it's kind of, your appetite for building these complex models will determine which route you want to go. So when do you want to build the custom model? In other words, when do you want to sort of graduate from the built-in Earth Engine classifiers and use something fancy? If you are using any of the softwares on the left, so if you like coding in Keras or TensorFlow or some other popular machine learning packages that are supported by AI Platform or Vertex, we have connectors for those. So that's an excellent reason to want to build these models. If you want to build something very fancy, like, for example, Dynamic World was just announced. Chris and Val in here, they built an incredible model. And it's very fancy. So if you want to do something like that, that's another great reason for wanting a custom model. If the size of your training data set gets very large, for the reasons that were mentioned earlier this morning, Earth Engine can have a problem with those very large data sets. They don't fit into cache. It can take the model a very long time to train on those things, longer than the 5-minute code editor timeout. So this is another excellent reason to want to go to a custom model. Did I just skip one? I got to use these buttons here. Okay. Okay, what happens if you have too much data? You can get an error. So as Noel mentioned previously, those tables may or may not fit into memory. And it depends on not only the number of points that you have in the table or the number of rows, but also the number of features. Feature in the machine learning context, not to be confused with EE.feature. Okay, if your table gets too big, if you can't export it in one single task to get it to some other location where you train your model, if you start looking at hacky solutions for exporting your data in a bunch of different pieces, that can be a problem because you can only run so many tasks at once. So these are all excellent reasons to think about going to a TensorFlow model. Okay, just to summarize, built-in classifiers, fast and easy to use, custom models, bigger training data sets, and more complex models with longer training times. Another great reason to want to build these custom models is if you want to implement a convolutional model. So in the left here, we have sort of a representation of a pixel-based classifier. So each pixel is considered differently by the classifier, and then each answer is too, but patterns are important. And these might be the patterns of rivers and roads and landscape features that are relevant to the classifier. You want your classifier to see those things. And it's more efficient for models to learn those patterns than it is to try to figure that out from a single pixel basis.
And that's it.
The weather model, should I talk about that?
I can say it.
Okay. Okay. AGV, take it away.
Yeah, so just as we move on from one topic to the other, the analogy here is if you actually are trying to do any kind of weather prediction, traditionally you're simulating every single atom, and that can get pretty big computationally and very inefficient. But if you instead find patterns, it's a lot better, and we have better models these days for weather prediction. So following that analogy, we'll dive into more about deep learning, which is finding patterns. So out of all the many ML algorithms out there, I'm happy to share that deep learning, or artificial neural networks, is a technique that can be used for almost any supervised learning job. In supervised learning, you tell the computer the right answers you're looking for through examples. And deep learning is flexible, and it's a very general purpose algorithm, especially for things like images, audio files, or video files, which are multidimensional data. A training model that classifies tree species, for example, using satellite images is kind of like an image segmentation problem where every pixel is classified in the image. However, there's more bands than the typical 3-channel RGB images. But deep learning approaches things very differently. There's no writing a function with explicit and sequential steps that reviews every single pixel one by one for the image, as traditional software development is done. So for example, in traditional programming, if you wanted to add logic to classify a new type of tree species to existing code, you can actually end up with, let's see if the GIF starts from the beginning, but basically Yes. So you're trying to add a new type of tree species to existing code, and then you start having a bunch of bugs because there's a lot of dependencies from your older code that you didn't really change from your instructions. And so at the end of the day, you might end up very frustrated and having to rewrite your entire function from scratch again. But with deep learning, you can really simplify things because you don't have to handcraft every single instruction. Based on that same example, you can actually give a computer images with tree species labels and let it learn from those examples. And when you need to add a new tree species, you just give it new images and retrain your model for that species. So now that I covered what deep learning, what it can help with and why it's more advantageous than traditional programming methods, I'd like to move on to how to approach a problem using it. So let's say we would like to measure deforestation using deep learning. Like many machine learning algorithms, it only understands tensors, which are numbers stored as an array or vector in one dimension, or a matrix or table in 2 dimensions, or as multi-dimensional data, which I was talking about, images, video, etc. So with that in mind, we convert satellite images into tensors, where each pixel has one number assigned for every satellite band. And to get started with building a model, we need, obviously, a data set that includes satellite images with an even amount of labels marking where there are trees and where there aren't. The next thing is we need to be really clear on what is our goal. And there are a few common goals. Regression predicts a number. Binary classification makes a prediction between 2 categories. Multi-class classification helps you classify things across multiple categories. Semantic segmentation classifies every pixel in an image. And in our case, we know we want to know if there are trees or not in every single pixel. So we're going to do binary to semantic segmentation. So based on that goal, we expect the outputs to be the percent of trees that are in every pixel between a number of 0 and 1. If you can imagine, 0 represents no trees, and 1 represents that I have a high confidence in trees. But how do we go from input images into probabilities of trees? So think about it this way. There are many ways to approach this problem. You'll notice that a lot in machine learning. That's just kind of brute force. You got to try all the things, etc. But to keep it very simple for you in this session, there are 3 common ways to do it. My peers and I prefer a fully convolutional network when building any kind of map with predictions. Why? Because they take neighboring pixels and they generate context for us. Remember those having to write every single instruction? Forget about that. It takes a context from the images automatically, kind of like our eyes do. And since a model is a collection of interconnected layers, we have to come up with an arrangement of those layers to transform our data based on our desired output. Each layer, by the way, has something called an activation function, which performs the transformations at every single layer before it passes on to the next layer. And my peer David's example, by the way, walks through everything about this. We're trying to keep it very high level to make it accessible, but I'll share the link in a bit. And so in regards to our deforestation use case, a good starting point is to have 3 layers, which includes a layer to normalize your data, a 2D convolutional layer, and a deconvolutional layer. Then you reach your 4th and last layer, and depending again on your goals, at the beginning, we choose something called a loss function that helps us score how well the model did during training. And FYI, since a lot of this is kind of brute force experimentation, we wanted to put a nice little table for you to visit, depending on your goal, which activation function to use and which loss function to use if this is helpful for you. You can later check this out, or if you're watching the recording, you can pause it or check the slides. And again, after choosing your layers, you will split your data into training and validation data sets, which I'll talk more about in a little bit. But just remember that all of this work is about just experimenting repeatedly until you reach your desired results. All right, so overall, that was a super quick summary to help demystify neural networks. I want to now dive into the products and the process of training a deep learning model and hosting it to make predictions. So, to get started, you will need an account with Google Earth Engine, which a lot of you know is free for non-commercial entities, and a Google Cloud account, which has a free tier if you're just getting started for any user. I wanted to break up the products by function first. So we have Earth Engine and Dataflow, and they're both data processors in this case. Dataflow is a fully managed service that executes Apache Beam pipelines on the Google Cloud Platform ecosystem. And then next we have TensorFlow Keras, which is an ML library, and Vertex AI, which is a machine learning platform on Google Cloud. And a quick note on that is I want to point out that Vertex AI is the latest ML platform for Google. Some of you may be familiar with its predecessor, Cloud AI Platform. If you are currently using AI Platform, no problem, but in the future, as you're creating new models, the product team recommends to use Vertex AI. AI Platform is currently integrated with Earth Engine, and we are currently working on the integration for Vertex AI. Then there's cloud storage, which is a bucket that we use to store and move data across the products. And just as a quick fun fact about storing files, depending on the ML framework that you use, you will typically work with TFRecords if you use TensorFlow, and you will use NumPy files for other ML frameworks. Then there's Cloud Run, and if you've heard of App Engine before, they're kind of siblings. And they allow you to kind of host any service, including your model. And finally, there's Earth Engine, again, to visualize your predictions, or Colab, which is a notebook created by Google research team, where you can use a map library called Folium, or any other type of mapping library, to be able to visualize. All right, and this, by the way, is just a quick screenshot in case some of you have never seen what Colab is, that notebook. You can write text in Markdown. You can click Run on snippets of code. You can enable ML accelerators like GPUs, and it's very collaborative. You can share it as a link. All right, so as we put all of these products together, let's move on to the architecture. So we built this design keeping in mind the inputs and the outputs. And our inputs are Sentinel-2 images and elevation, and our outputs are land cover. And sure enough, what we're trying to do is land cover classification. If you want to take a quick picture of this, or later visit it in the slide deck, but basically this is that end-to-end sample that my peer David made for y'all for this event especially, that takes you all the code, all the way from starting and understanding terms in machine learning to visualizing it in Earth Engine using AI Platform. Is that okay? Yeah, all right. We begin, so after we establish what our inputs and our outputs, and we now want to pull that data from Earth Engine, and we use that with Dataflow. And we get a collection of input and label pairs, and we save them as TFRecords. And the reason why we use Dataflow, by the way, we could use just Earth Engine, but we noticed that if your data set is very large, it can take days or, and luckily maybe hours. So if you really want to reduce it to minutes, Dataflow is your best friend for that. Next, we save those as TFRecords into cloud storage. And then we split our data into two data sets. 90% is for training the model, and 10% is for validating that it learned from examples it has never seen before. And then we train that in Vertex AI. Note there's no hard and fast rule if it should be 90-10 or 80-20. You get to choose that. We just chose 90-10. Also note that the process of splitting the training and validation data set can be at different stages depending on what machine learning framework you use. So just in case you're like, I've seen it at this stage or that other stage, it's up to you. There are pros and cons, and the notebook actually talks about that. If you also want to not use Vertex AI and train on your computer, you could do that. Just know that depending again on that size of your data, it could take a very long time. All right, so after we train the model, we store it into cloud storage as a TensorFlow file called saved model. And we can then host that model into Cloud Run and begin to classify incoming land cover labels. So you'll see that there's a difference between training and hosting the model. Now, in the event you want to eventually change your model, you want to make some tweaks, you can use Dataflow to do that in batch, and it'll change all your historical labels. And then you can go back to using Cloud Run for streaming those predictions again. You can also host the model locally on your computer or Colab notebook, by the way. So there's a couple of options for that hosting part. The most important question for a lot of folks is price. So I just wanted to leave you that, we have I co-created a YouTube series. Every episode is about 10 minutes. We just dive into machine learning, usually with Earth Engine and Google Cloud. And of these recent episodes, we've noticed as of October 2022, it's cost us less than $5 to do that from end to end. However, the reality is that most of you want to connect a model back into Earth Engine, and so I wanted to just share 2 more steps. The first is you can, instead of hosting it in Cloud Run, you can actually host it into AI platform, which is integrated with Earth Engine. Just know, though, that it's a 24-hour paid service, and so it can cost you upwards of $100 or more a month to host your model to stream predictions. AI platform supports TensorFlow, scikit-learn, XGBoost, and it can also do PyTorch if you use a custom container. Also, just be mindful of the zoom level, because that can also affect how many requests you're sending. Now, a cheaper alternative to AI platform, although you will not have the convenience that AI platform offers, is to manually translate the model's output, which is NumPy arrays, into cloud-optimized GeoTIFFs in order to load it back into Earth Engine using Cloud Run. So there's a little bit more of a breakdown. So within this web service, you store the NumPy arrays in cloud storage, and then you spin up a container, and by using GDAL, which is an open source geospatial library, to convert the cloud optimized GeoTIFFs into cloud storage again. And this way you can view predictions from Earth Engine or from your browser. And by the way, we have a sample coming. We know that's very important for the community, so stay tuned. We're working on it. And this is also another resource that I'm not going to go through right now because it's just a lot. But if you're trying to kind of go through branching logic of what to use based on your use case, that's my attempt at providing that. All right, now I'll pass it on to Nick again, who's going to give you a demo.
All right, thanks. How are we on time? Not too bad. How many people are checking email? None. Sweet. Okay. Oh, one. Couple. All right. Whatever. That's okay. All right. So as AGV was saying, we've got this sort of end-to-end notebook that really enumerates every possible combination of cloud services and data extraction methods that you want to use. There's I linked to the previous version in here. Next version is coming soon. Those were both done by David Cavazos. And he and I kind of had dueling banjos on this. So the examples I'm going to show you are like simplified versions of that. Okay, step one, get stuff out of Earth Engine, get your training data out of Earth Engine. Option one is you export tables. And there are lots of docs on that. See the TensorFlow page for more info. There's the REST API, so if you want to make calls directly to the REST API and just get blocks of pixels as NumPy arrays or JPEGs or whatever you want to do, you can do that. And there's an example for that in our docs. You can get patches with get download URL, which is somewhat different than what we've done previously. And you can scale that with Dataflow, which makes it a really nice option. Coming soon, there will be a client-based compute pixels, which is even lighter weight than get download URL. Not quite ready yet, but coming soon. Okay. So example number one is a fully convolutional model for semantic segmentation. We want to go from some set of input bands to a label in every pixel. And how do you do that with TensorFlow? This is the demo Colab that's going to run through this example end to end. So you can grab that Colab. It's not going to work right out of the box because you have to substitute your own cloud project and your own cloud storage bucket. But once you do that, all the code should work. And please let me know if that link doesn't work or if any of the code doesn't work. All right, so this is the goal here. And the first step is to sample some patches. So in the morning session, if you were in there, you saw how to sample pixels. And Noel showed you some workarounds for getting neighborhood information in there. You can use neighborhood to array or neighborhood to bands or compute gray level co-occurrence matrices, that kind of thing. But you're not going to get patterns that way. And so the idea here is that we want to sample patches out of here that contain spatial patterns. And we're going to do this as 128 by 128 patches with 9 bands or something like that. And these are just some regions that I drew by hand. We're going to sample 128 patches from each one of those images. Oh, by the way, where is it? I already revealed it on the next slide, so I forgot to play that game. Sorry. All right, it's near Ho Chi Minh City in Vietnam, and so we're going to go into some code now, and I'll just walk you through this. The idea here, oh, do I have a laser pointer? Sort of. Okay, the idea here is that you want to take a sample of random locations from those polygons that you saw on the previous slide. And an easy way to do that is stratified sample. That will give you approximately the same number of points in each class, which is good. It will try the landscape distribution may be very imbalanced, but stratified sample will attempt to get you a balanced training data set. And then at the end here, all we're doing is calling getInfo. First we convert the sample to a list and then call getInfo on the list. And what that does is that moves the sample from the server to your client, which in this case is the Colab Notebook virtual machine. Once you have that sample on the client, you can iterate through it or make it into an iterator or a generator and yield each set of coordinates one at a time. So this thing is just a function that yields coordinates one at a time from those boxes. Now, we get this set of points, and what we want to do is we want to get a patch under the points. So one way, in our docs, we show you neighborhood to array, and then you export that. Here's another way. This way uses get download URL on your image of predictors. So the image that you saw on the left, which had spectral data from Landsat, I think it was Landsat. No, maybe it was Sentinel. I don't even remember. Anyway, you get spectral imagery. You call get download URL. At your point, you tell it the size of the patch you want. You tell it you want a NumPy array, and that's it. You can use whatever request library you want. It's a GET request to the Earth Engine service, and then you load the result into a structured NumPy array. And all this is happening on your client. Okay, so the advantage of this is that you can connect to the high volume API and send a lot of requests. And if you're using tasks, those tasks can get too big. As AGV mentioned, they can take days to finish, which is not always ideal. And you can only run so many of them at a time. So this gives you a potentially more scalable way to generate a lot of training data. Next, please. Yeah, thank you. Oh, can you go back one? Sorry. The other thing that I'll mention is that this function is retryable. Batteries are dead. The function is retryable, the top line there. What that means is that you only get a certain number of requests at a time. When you run out, you have to wait for one of the previous ones to finish, and then you can do another one. And by decorating this function with retry, that will happen for you automatically. So that's another advantage. Next. OK, this is what it looks like. This is our patch of Sentinel-2 data. And it has a shape of 128 by 128 by 9 bands. These are the bands that we're going to use for prediction. There's nothing scientific about this. I'm just using these bands for demo. And then, whoop, previous one. OK, thank you. The labels are from WorldCover. And so all we're doing here is we're just getting labels from an existing land cover product and using those to train a model. If you're doing something fancy, you probably want to collect your own labels somehow. But we assume that you have a set of inputs and a set of labels, and you want to predict those labels from the inputs. Next, please. OK, before you can send those patches into TensorFlow, you have to serialize them. Or at least this is an efficient way to get those things into TensorFlow. And so the point that I'm making here is that so the array that you get from get download URL is a structured NumPy array, which means that you get the bands out by just using their name to index into that array. So you get the name from the array. You shove it into a tf.train.example, and you serialize it into a string, and that's it. So this is just converting blocks of NumPy float data into a serialized format that TensorFlow can read. Next, please. OK, now we can put all that stuff together into an Apache Beam pipeline. And the big advantage of doing this is that you can send that pipeline to Dataflow and run it at scale. So that's why I'm showing you this crazy stuff about, serializing patches and NumPy arrays and so on and so forth. Because eventually you want to write something like this and send it to Dataflow and run it at scale as an alternative to exporting those patches. OK, so how does this Beam pipeline work? First, you just create the pipeline from those regions. That capital regions is that list of the polygons that I drew near Ho Chi Minh there. Then we're going to do a flat map over those regions. So this is like calling a map in Earth Engine and then .flatten on the result. You're going to flatten out the multiple things that come from sampling this region. So each region gets sampled. And remember, this is where you're yielding those patches. Or sorry, you're yielding the coordinates one at a time. And for each coordinate that gets yielded, you grab the training patch, you serialize it, you split it into 2 pieces, write it to TFRecord, and that's it. So this pipeline is sampling all those polygons, grabbing a patch at each sample, serializing them, splitting the data set into 2 pieces, and writing it to TFRecord files. OK, next. OK, let's see. Right, so I'll call your attention to our handy little graphic at the top here, which indicates which stage of the process we're at. We've generated our training data, and now we're going to pre-process the training data. So you've written your Beam pipeline, you ran it with TensorFlow, you've got a ton of data sitting somewhere or other. Now you want to read the data. That's what this thing does. And there's a bunch of fanciness in here. You interleave the reads, so the reads get parallelized over the files. You read them into TFRecord data sets. You parse the data out of them, because remember, we put those into those serialized strings. Now we're going to parse it back out again. Cache it, shuffle it, batch it, and prefetch it. All this stuff, if you go to the example notebook, it links to the TensorFlow docs that explain why you might want to do all this stuff. But the idea is just to have a very efficient pipeline for reading the data sets that you wrote. Next. OK. Now we're going to define the model. As I mentioned previously, this is a fully convolutional model. And so what are we looking at here? First of all, I'm not a deep learning expert, despite the title of this talk. I took a class at Google once, and the teacher said, grad students have wasted the best years of their lives generating these models so that you don't have to. And I really buy into that philosophy. So, you know, your fancy model stuff goes in the middle there. You know, this is just something that I grabbed from the image segmentation by scratch page on the Curious website. That's what this model, the fancy stuff, is in the middle there. You know, substitute your own fancy stuff. OK. The important point that I want to make here is about the shape of the input and the shape of the output. Specifically, the input shape is going to be height by width by channels. So note, I've left the first two dimensions, the height and width of the patch, blank, so that you can use whatever you want at predict time. But the model is trained on 128 by 128 by 9 patches, and you are expect to have 9 inputs here. So the patch size can vary, within constraints of the model architecture, but it's gonna expect 9 bands. So that's the length of input bands here. So height, width, channels on the input. On the output, you have another convolutional layer with the number of classes in your output as the depth. And what that means is that you will get a number for each of the classes in your classification. And that number is the predicted probability that that's the class that you're seeing in that pixel. So you will get a 128. Oh, do we have a quiz on the next one? Can you go to the next one? OK, no, go back up. Sorry. Pop quiz. What is the shape of the output here? It's kind of a trick question. It's kind of a trick question because really the shape is whatever shape you send in with 9 bands. You know, so it's height, width, 9 bands deep, and the output is going to be the same shape, except the depth is going to be the number of classes in your classification. So that's what is coming and going out of this model, and that's what we have to tell Earth Engine to expect. Next slide. OK, now you've got your fancy model. You've got all your training data. It's time to train your model. You can train it wherever you want. So in this example, it's just trained in the Colab Notebook virtual machine. That works fine if you've got a small model without too much training data. But if you have a big fancy model with lots of training data, you might want to use some cloud infrastructure to do your training. And you can find that in this second example here. That will train the model on Vertex AI, which will let you do much longer training jobs, hyperparameter tuning, lots of fancy stuff like that. Or you can use a deep learning image, which fires up a VM for you, which has all the right software already pre-installed in it. You start up a Jupyter Lab server on the deep learning VM, connect to it, and then do your thing that way. It's like Colab, but you have control over the size of the VM that you're using. So that's another method. Or you can train it on your big fancy university cluster or whatever you've got. Maybe you have a very good machine that you can just let it run for a while. That's fine too. At the end of it, what you're going to have is a trained model, and you're just going to save it to saved model somewhere in cloud storage. So you can train it wherever and however you want. All you have to have at the end is the saved model. Yes? Yeah, so the question is, if you're training on your big fancy cluster, you've got to get the data to your big fancy cluster somehow. And the way you're probably going to do that is you're going to stage it in a cloud storage bucket and then download it. So yeah, you still have to get the training data to your machine somehow. Other questions? How are we on time?
You have 20 minutes.
20 minutes, plenty of time. Okay, this is another new part. Previously, we did a thing which we liked to refer to colloquially as eification. And really, it should have been called AI platformification. But that was implemented by this Earth Engine model prepare thing. And the purpose of that was to bolt on some extra nodes to your saved model. So you've trained your model, you saved it, and now you want to send things back and forth to Vertex AI or AI platform, and those things that you send back and forth need to be base 64 encoded. And this Earth Engine model prepare command, the Earth Engine model prepare command did that for you. It bolted on those extra nodes that would do the conversion from float 32 to base 64. Here's a programmatic way to do that. So basically, this is extending tf.keras.layers.layer. So you're defining a new layer. And inside this new layer, when you're deserializing your input, you decode base 64 and parse the tensor out of that using the features that you know are supposed to be in there. And that gets sent to your model. On the way out, you encode it to base 64 and serialize it, and that's it. So this stuff, you'll actually find this in the open source of the Earth Engine Python client. So you can look that up on GitHub. You can see the source for Earth Engine Model Prepare. That's basically what this stuff is doing here. But it's doing it the new way, the TensorFlow 2.x way using Keras. In fact, an external user figured this out. Matt Miller, shout out to Matt Miller. Thank you very much. This is how you do eification programmatically. Okay. Next slide, please. Okay, I lied a minute ago. You don't save your model first. You do the eification, then you save your model. You can also do it in the reverse order. In fact, that's the second demo. But for now, you define your fancy model, you wrap it in those extra layers, and you save it. Next. Okay, now we want to connect to it from Earth Engine. And the way that you do that is you host your saved model on AI platform Vertex coming soon. So here we're just creating a version and pointing it to the directory in cloud storage that has the saved model artifacts. So I'm not showing you creating the model. First you create the model, then you create the version. You point it to your code, and next slide. Then you connect to it using this Earth Engine connector in the client library, ee.model.fromAIPlatformPredictor. Now, the important thing with this is, well, I tried to bold the important things, but really all this is important. So first, you specify the project, the model name, and the version name. Then you choose a projection for your input data, and you set fix input projection to true. Why do you do this? The reason that you want to do this is because when you've sampled your training data, you've chosen a scale and projection. If you export something in Earth Engine, you set the scale and projection, right? If you don't set that, who knows what you get. In fact, you'll probably get EPSG 4326, 1 degree by 1 degree scale. That's probably not what you want. We want EPSG 4326, which is just latitude, longitude in WGS 84 at 10 meters resolution. And we fix that input projection so that when Earth Engine is sending tiles to AI platform, it's sampling the tiles in that projection and at that scale, which matches your training data. So that's why we do that. That's also why AGV told you not to zoom out too far, for the same reason that if you zoom out too far with a reproject, Earth Engine will try to get every pixel you can see in the thing and reproject it. So if you zoom out to the whole world with your model, it's going to try to sample the entire world and send all those things to AI platform, and sadness will ensue. So don't do that. But you can export this stuff. The other thing is you set the input tile size, and recall that I mentioned previously these models are invariant to input size within some constraints, but this is basically half the input size. But then I'm doing this other trick, which is specifying the overlap size. So it's going to overlap 32 pixels on every edge of the patches, and that's great because sometimes you have edge effects, and you have to trim those out. So this is a nice way to sort of fiddle with, you can think of all these as hyperparameters almost. And you might want to tune the patch size and the overlap and all that stuff to get the best accuracy. Any questions about this? Yes? Yeah. Fascinating question. You would not specify a fixed input projection in that case. You would let Earth Engine figure it out for you. And right. So I think the question is, can you use scale as an input to your model? Fascinating question. I don't know the answer. There might be research on that topic. If not, then there's fertile ground for research right there. Okay, next slide, please.
How long does it take to register the model in AI platform? Because hosting is costly, right? So if you register and unregister, it's actually saving money if you can do that quickly.
Yeah, can you go back to the model creation, the previous one? This. Okay, yes, thank you. This is a paid service. And when you spin this thing up, you're going to start getting billed for it. And so the idea is, you spin it up, do your predictions, and then you turn it off again. But you will get billed for making those predictions by a hosted model. And furthermore, if you attach GPUs to it or something like that, you're going to get an even bigger bill.
Yeah.
So it's very slick, but it is a billable service.
So if you remember, training and hosting, two separate workflows. The reason why training, for example, in our samples were less than $5 was because we turned it on real quick and we turned it off and we called it a day. But Vertex AI or AI platform are services that have a VM that's on all the time. And now we're talking hosting. So in order for you to get streaming those predictions, that's where it starts getting costly because there's a cost per hour. And then there's an additional cost per hour if you enable an accelerator called a GPU.
Okay, I'm going to move on because we're running short on time here. This is what you get. This is the input. This is the output. You call predict image on the input. You get that vector of probabilities that I mentioned before. And if you want the class label, you call array argmax on that image, and then you get the label, and then you get your patch. And this is the result of my not fancy model at all. So, next example. This is a convolution. This is an image classification model. So, patch goes in, label comes out. This is a very different thing. This is not, patch goes in and patch comes out. In fact, you're reducing the resolution of the input here. I sort of struggled to find suitable training data for this. In fact, I've been doing some beaver research recently, which I've got this great presence-absence data set for beavers. That's really what you want for this kind of thing. Patch goes in, what's the thing in there that you're looking for? If you have that data, great. Here's an example of sort of a pre-baked model that does that. This is the Big EarthNet model. This was, the data set is a bunch of Sentinel-2 patches that were labeled in terms of what's in the patch. And a guy, a Googler actually out of the Zurich office, took that data set, trained a ResNet 50 with it, and hosted it on TensorFlow Hub. So what this ResNet 50 does is it takes 120 by 120 patches from Sentinel-2 as input, and it spits out the list of labels of stuff that you think you're going to find in there. Airports, beaches, rivers, water bodies, all this kind of stuff. So that's what this model, it's just a pre-trained model, a pre-trained image classification model. So the problem with this pre-trained image classification model is that the results, you need to EEify this thing. And so here's how that happens. Is that happening here? No, it's not. This is just the model itself. You do have to EEify it. This is just the model itself. You go to TensorFlow Hub and you grab the URL. You load the saved model from there. You say, I want to use the default serving signature to make predictions, and I want to get the logits out the end of that thing. There are a bunch of outputs from this model, embedding vectors and all kinds of fancy stuff that might be useful to you. I just grabbed the logits, stuck them in a softmax to get probabilities, and now reshape the outputs. So this is the part that is to make this model work with Earth Engine, and specifically, so here are the probabilities. This is just a length 43 vector. 120 by 120 patch goes in, length 43 vector comes out, but we need to expand the dimensions of that thing so that it is pop quiz. What shape does it need to be? Okay, so in this case, it will be the length of this vector, which is 43, 1 by 1. So 120 by 120 goes in, 120 by 120 by 3 goes in, 1 by 1 by 43 comes out. And so that's the real point that I want to make here, is that Earth Engine is expecting data in this specific shape so that it knows how to put it on the map. Next slide, please. Okay, so You define your model that way, you EEify it, you save it, you host it, and then you connect to it. This connection is a little bit different, obviously, because it's a different kind of model. Specifically, I'm fiddling with the input tile size and the input overlap size here. Just again, these are almost hyperparameters. I'm not sure what they should be. I just kind of fiddled around with this thing. Sometimes Earth Engine will complain if you don't tell it the shape of the input. And specifically, what it wants to know is that you're sending an array in, and it's a length 3 array, meaning red, green, and blue. That's what the big EarthNet model is, red, green, blue. That's what it expects. And the output tile size is 1 by 1. So what's happening here is that 120 by 120 at 10 meters resolution is coming in. 600 meters is coming out. And in each one of those big 600-meter pixels is the length 43 vector of all the things that it thinks is in that patch.
5 minutes.
Next slide, please. OK, so this is what the output looks like. This thing goes in. Each one of these is a 60 by 60. Each one of these is a 60 by 60 patch. You can't see the overlap because that part gets chopped off. But it thinks that in this patch here, there's some, list of 43 things, some of which might be, vanishingly small probability. So I made this little app which just shows you the top one, but there's a list of them in there. Next slide. OK. Am I taking us home? You're taking us home. OK.
Do you want to say anything?
Any questions about these demos before I? Yes, in the back there.
Is it typical for like the pre-built model to have documentation?
Depends.
Yeah. Is it typical? I'm not sure.
Depends.
This one had sort of mediocre documentation.
The question was, do these lovely on-demand models have documentation? And the response is, depends on the author.
Right.
Is there a way to estimate costs for predicting a large part of that?
Yeah. The question is about how much does it cost? I don't have a terrific answer for you. But in developing these demos and running a lot of predictions sort of over that small area, I racked up about a $200 bill in a month.
For AI platform.
For AI platform.
But if you try to do where you transform the NumPy arrays into cogs, it could be different on Cloud Run.
You want to take us home?
Yeah. So please take a picture of this or visit the resources. This first link is David's end-to-end sample. It defines everything that Nick just walked through and a lot of canonical best practices. These are 2 of Nick's beautiful demos that he built just for you for this session. And I think you call them more simplified specific areas. One's a fully convolutional network, and the other one is using an existing model that you pull in. I have my People on Planet AI series on YouTube. We will be launching in a couple of weeks, this same content. That we also are going to talk about weather prediction. Then we're going to do wildfire prediction. And then we're going to talk about restoration as well, all through fully convolutional networks. And then if you want to stay in touch or stay connected as we are bringing out content, you can follow me on Twitter at OpenEcoSource or the Earth Engine Twitter account as well. And I believe, Nick, you wanted to say something about this?
Yeah, so we did pitch this in the previous session as well. It would be great if you would like to take part in a user survey, as we build out this infrastructure, understanding how people are using it and how they want to use it and where the pain points are. Is really valuable to us. So if you'd like to participate in the study, please fill out the form, and someone will be in touch.
Yeah, I'm blown away and impressed at how many people are in this space. So definitely, if you're here, make your voice heard in this form. Anything else? Thank you for being here. Have a good day.
Thank you.